to this. And so the picture you should be thinking of in your mind is if omega is convex. So here I'm going to pretty much work in R2 just because it's easiest for us to do calculations, but most of these things work out in, well, some of these things work out in Rn, and I'll try and give pointers to where everything goes through. So here's, well, I'll draw it as Rn here. And so our domain is some kind of omega down here, and the graph of our function looks like this. And we consider the level set. So these are the sets where our solution all has the same height. So we have something like this. So I'm going to write the level set as, let me back up a little bit. Let me consider the super level set. So this is going to be given by omega c, and this will be all the points in the domain which sort of take on a value that's greater than c. And the question is that also convex? So if we think about this little picture here, we can sort of project that back down to the plane, and we get another little set in here, and that's our super level set. And we could imagine if we just drew omega itself. So here's some set omega, then the boundaries of all those level sets might be sort of these concentric sets. So the question is, you know, when is this true? And the sort of answer is kind of infuriating, because the answer is this is almost always true. Sorry, I should actually mention, when we go back to our problem, another condition here is that f is positive or non-negative. Yeah, so we expect our solutions to look something like this, and people have looked at this a fair bit for different values of the right-hand side f, and they've found that, you know, for almost all the f's that they look at, this pretty much always holds. So I'm just going to mention some classic results. So for example, in the case that f of u is equal to lambda u, then the problem's just the eigenvalue problem, and use the first eigenfunction. And the property holds. And this is due to Braskamp and Leib. in 76. And this turns out to be a really important property, particularly in the theory of probability. You'll find that a lot of the results in this area are sort of done in a very probabilistic language. There's sort of a more general result if, say, f of naught is equal to naught and f is non-decreasing as a function of one variable. This is due to Caffarelli and Sprook. I think in 82. And there's kind of a whole industry of finding these kind of results. And that would sort of be nice if it was always true, but the reason why it's actually intriguing is there's also a counterexample. So this is quite recent, and this is sort of what made me a little bit more interested in this problem in itself rather than as a tool for finding other results. And this is due to Hamel, Nadarashvili, and Sear. And they actually just constructed a very explicit domain and a right-hand side G, and their domain was some kind of very long stadium shape. And what they found is on this kind of shape, the level sets, because it's such a long and narrow shape, they're kind of almost flat, but they were able to choose this G in such a way that kind of had a little, a little non-convex part. So out towards the boundaries, these are kind of quite regular, but there was just one sort of very small part where there was a little dint in the boundary of the level set. So that's why this problem is quite intriguing, because it still hasn't been proven where this dividing line is between problems that have this property and problems that don't. And so a plausible conjecture, which they mentioned in this paper, is that the property holds when U is a semi-stable solution. And this means that for all test functions, we have the Dirichlet energy minus f prime u phi squared is positive. It's greater than or equal to 0. And so the idea is that when this is kind of a variational solution, it sort of minimizes an energy, then you should get the property. And this counterexample doesn't satisfy that. So yeah, that's sort of the motivation and the interest there, and where I'm coming from. So feel free to ask me any questions here. And I should also say that I wrote some notes for this, but they're kind of in a disgraceful condition at the moment, so then I'm not quite ready to share them, but I should be able to tomorrow. Okay, so this is going to be what my plan is I'm going to talk about just the sort of background and the notation. So maybe notions and notation. Then I'm going to talk about the eigenvalue problem. This is kind of the simplest case. Whoa. And then I'm going to talk about the general case. Sort of for a general right-hand side. And then I'm going to take a step sideways and look at this in a geometric setting on a manifold. And talk about some recent work that we've been doing in negatively curved spaces. So that's where I'm going with this. I should mention that also that this has been, fairly well studied, and maybe the nicest treatment of it, but it's very old, is the book by Cavol on rearrangements and level sets for elliptic equations in PDE. I think it's called that. Rearrangements and convexity of level sets in PDE. It's just a short section at the end of the book where he talks about these things. But also this Hamel-Nadarashvili Sai paper, it's got a really good introduction and it outlines some of the issues. Okay, so let me move on. Okay, so I'm going to be talking about two different kinds of convexity or concavity here. So we all know that a convex set is one in which, when we have 2 points in the set, the line between them is also contained in that set. So and we can also extend this to a convex function. So this is when the epigraph, so the set that lies above the graph, is a convex set. So for a function of one variable, it'll be like that. But I'm going to be really not paying very much attention to regularity here and assuming that everything is quite smooth. So for a C2 function, we say this is convex when the Hessian's positive semi-definite. Okay. And we also have concave functions. Now, if we go back to looking at our original problem, in general, the solutions to this are not concave. You know, if we're on a ball, for example, this is not true, then things really are concave. But in general, concavity is much too strong. And so we've got some weaker notions of concavity here that will do for us. So let me just write that down. So and I didn't give my main problem a label, so let me go back and fix that up. Let's call our problem star. Okay, so let's write some other notions of concavity, which are ranked. So firstly, this is the strongest. So F is concave. Okay, so if it's C2, then the second derivatives are negative semi-definite. This is a little bit weaker, and this is called alpha concavity. So F to the alpha is concave. So for some alpha in 0, 1, sort of the zero case of this is when log F is concave. So this is called log concavity. And the final notion is the one that is the weakest one and the one we're going to be looking at. And this is that F is quasi-concave. And this is exactly the property that the level sets are convex, or the super level sets. And Yes, so these are completely ordered. So this one implies all of those. And you can see that this quasi-concavity property is really, really weak. So for example, if we have any radially symmetric domain, and a radially symmetric solution, then all the level sets are going to be balls or spheres. Well, let's just think about 2 dimensions and say all the level sets are circles. But we could imagine that this might not actually be concave. So we might have U of R might look something like, like this. Yeah, so this quasi-concavity notion is really very weak. Right. So what I'm going to do now is just talk a little bit about the geometry. So this is really sort of well-known things, so feel free to, zone out a bit. But I should just mention what's going on here. So when we have such a solution U, clearly the shape of the level sets is completely given by U, but we kind of want to deal with the level sets as objects in themselves. So let's consider our domain and our function. So this is what we're expecting our function to look like. Some kind of turtle shell. So if we consider a level set up here, we can draw this down in the domain as some kind of level set. So this here is supposed to be the graph of U, and this here is supposed to be the level set. And what the implicit function theorem tells us is that we can always find a little parameterization of this level set at any point where the derivative is non-zero. And what I'm going to do is I'm going to write the level set the parameterization of the level set as some curve gamma. So we're going to write this as gamma of x. And so this will be from a little interval in R to R2. And this has a normal and a tangent. And it also has a curvature. Which usually for parameterization would calculate this as the derivative of the unit tangent but we don't need to have a arc length parameterization here. We could have just in terms of whatever our parameterization up here is. And so this would be dd x of t in the direction of the normal times dx ds. And here dx ds would turn out to be 1 over the absolute value of the derivative of our curve. So the reason I'm doing this is because I want to relate what's going on with u to the curvature. So I'm going to calculate some derivatives of u. Okay, so since gamma is a level set, so we have u of gamma of x is equal to a constant. And so we have du, so taking the derivative of both sides with respect to x gives us du gamma x is equal to 0. So this is du is in the direction of the normal. And gamma x is the tangent. So when we take the dot product of this, it gives us 0. And we can also take second derivatives here. So we get d2u. Now I'm going to write this as the Hessian. So this is going to be a d2u of acting on gamma x. So in coordinates, if you prefer to write it that way, this would be like d2u dx I dx j gamma prime or gamma x I gamma x j. So this would be d2. Yeah, this would be the matrix entries here. What am I doing here? Oh, I'm taking the derivative of this guy. But we also need to take the derivative of this tangent vector. So we get this. And so now let me make my screen a bit smaller so I can fit a little bit more in. Now I'm going to sort of go back to my curvature here and just sort of follow the calculation through a little bit more. So this is going to be ddx the tangent is like this, and because I'm dotting this with the normal, I don't need to worry about taking the derivative of the length here. And what I'm going to get is a 1 over gamma x squared, gamma xx dot. The normal here is, again, du divided by the length of du. And the reason why I write this is because I wanted to sort of recognize this part here and this part here are the same. So here we've kind of managed to pick up our curvature in terms of u. So this gives us that d2u is equal to minus kappa, and got some, whoop, and here's a du there. And maybe we write everything in terms of the unit tangent. Okay, so this is kind of a fairly natural identity. So if we think about our problems, this is telling us the curvature of the level set. And the sign of the curvature of the level set is given by the sort of one component of the Hessian, and the component of the Hessian that's purely in the direction of the tangent. And this is kind of natural when we think about our picture up here. If we consider all our level sets, then we can see that the level sets are not containing all the information about you. They're just containing, they're just containing part of the information, because you could have a different function for you here that had exactly the same level sets if it was changing direction in the direction of the normal at a different speed. So the part of the Hessian of u is giving us the curvature. And this also gives us sort of another way to think about the problem. So our original problem, which you've probably all forgotten it, so write it down again. If we think about our original equation, then if u satisfies this equation, then this on the one hand is saying that the trace of the Hessian is negative. So the Hessian is this matrix that has negative trace, and what we want to know is one particular, oh, I just saw your message that said the sharing stopped.
No, but that was fine. It's just I think one person had a problem.
Oh, okay.
But it's working now.
It's okay. Great. So the trace is negative, but we really want to know about sort of one specific component, whether this is also negative. So yeah, it's kind of, it's almost there. It's not impossible that the curvature should be positive, but it's also not directly given. So what we need to do is use that extra information that's given by this being a solution and a domain being convex, and get some kind of global properties going on there that will give us that sort of extra extra bit of information that will go from saying, okay, this trace is negative to actually this component is negative. So hopefully that makes sense. And it did say that I would say what's going on with higher dimensions. You can of course do this in higher dimensions, and you get you can do this for the mean curvature. And the question there is are all the curvatures of your level sets positive? Right. So I should maybe connect up a few dots a bit more. If gamma is the boundary of a convex set, then kappa is positive or non-negative. If kappa is positive, then we say gamma is locally convex. But this doesn't imply that it's the boundary of a convex set, because we have you know, curves that might look like this, which are locally convex, but they're not the boundary of a convex set. Good. And now that we've made this calculation here, we can observe that log concavity will always imply quasi-concavity. So if U is log concave, then U is quasi-concave. And we can just do that. So suppose this means that log of U but we can calculate what's going on with this f equals log U, because we have df is equal to du divided by u. And here we recall that u is positive on the interior. So this is okay. And in fact, we can, for solutions to these elliptic equations, we can show that this is well defined up to the boundary. Well, it's not. It's well defined up to the boundary. And on the boundary, it becomes unbounded. Anyway, we can calculate the second derivatives of f, and this is given by the second derivatives of u minus 1 over u squared sort of vector product of du cross du. And now if we know u is log concave, then we know that D2F is negative semi-definite. And now let's go back and remember what our curvature was. So we have D2U in tangent directions is going to be given by U D2F in tangent directions plus plus 1 over U du, also in tangent directions. But now we realize that du here is a normal direction to the level set. So all of this part here will cancel out. And this is equal to minus kappa du. So what we've found is that if this D2F is negative semi-definite, then this means that our curvature must be non-negative. So that's sort of a short little calculation that lets you see that this log concavity is certainly sufficient to show the quasi-convexity, the convexity of the level sets. Okay, so any questions so far? Okay, so let's move on. Okay, so let's start talking about some specific equations. And one that's really nice for me is the eigenvalue equation. So our equation now becomes like this. We're going to take Laplacian of u, but now I'm also going to consider a potential. So here, V will be a convex potential. So it's just a convex function that's defined on our domain. And here we've still got our 0 boundary value and our positive function on the interior. And once we've set up our problem like this, the general theory of eigenvalues tells us that there's exactly one lambda that satisfies this, and that lambda is the eigenvalue. Okay, so for general, so if you think of some random lambda here, it doesn't necessarily have solution, but there's exactly one lambda where it does have a solution. And I guess u is the eigenfunction. And because this is the positive one, There's many eigenfunctions, some of which, well, most of which will change sign, but because this is the one that doesn't change sign, this is also called the ground state. For the physicists. And so this problem comes up a lot, and it's of physical meaning, and it's also used a lot in probability. And the result here is due to Braskamp and Lieb. So their result is that if omega is convex, then U is quasi-convex. Quasi-convex. I always get confused when I write quasi-convex, so I'm never sure whether it's quasi-convex or quasi-concave, because it's a concavity property, but it's talking about the convexity of the level sets. And this is quite an old result, and there's a lot of really very nice proofs of this. And I'm going to sort of present one that's due to Yao. It's in a paper by Singer Wong, Yao and Yao. So yeah, that's what we'll do. Maybe I'll give you some examples first. This is a really easy one. The nice thing about this problem is that it's one you can give to your engineering students and tell them to solve it by separation of variables for some really simple domains. So if we take a box as our domain and a zero potential, then we can explicitly write down the solutions. This is given by U equals sine of x pi on A, sine of y pi on B. And you can check that U is log concave, but not concave. And just now that I've written that, I realize I've kind of somewhat undersold Braskamp-Lieb's result. Maybe I write the stronger thing here. U is log concave, and hence quasi-concave. And another similar example here is the case when omega is a ball, and you can even give it a potential here. So let's write V of x is x squared. And because this potential is purely radial, we can solve in polar coordinates by separation of variables. And when we do this, we get an ODE for U just as a function of R. And we can use ODE techniques then to show that it's concave. So we actually get concavity for this one. And yeah, U solves an equation that looks a little bit like the Bessel ODE. Yeah. Okay. So this, let's write this. Let's call this one BL. And this is the proof of BL. And this is using a method of Singer, Wong, Yao. So there's, as I mentioned, there's many different proofs of this. This is from a paper in the early 80s. There's also some nice proofs of this due to Curvature and others. So what we're going to do here is, sorry, I'm just finding my notes. There we go. Okay, so let's just consider f, which is going to be log of u, and use the eigenfunction. As a positive function, we can define the log of it. But we should expect it to look like if we took a slice through our domain like this, and we have u looking like this, then f would look something like well, too closely to the edge there. So f's going to be unbounded towards the boundaries, and it's going to have unbounded derivative as well. So we've already looked at this, but I'll write it down again. So the derivative df is given by du divided by u, and the second derivatives of f are given by the second derivatives of u minus u squared du cross du. And in fact, we can write this as 1 on u d2u minus df cross df. And so since u satisfies the eigenvalue equation, f will satisfy something that looks pretty similar. Laplacian of f is equal to lambda minus v plus df squared. Okay. And we also have the boundary conditions. F of x going to minus infinity as we approach the boundary, and df also becomes unbounded. Okay, so what we're going to do is we're going to try and show that, firstly, that the Hessian d2f is negative towards the boundary, and then we'll show that it can't have an interior positive maximum. So a kind of a maximum principle type idea. So this is what we're claiming, is that well, so we're claiming that f is concave near the boundary, and we'll just do this by taking a orthogonal basis and what we are going to observe is that on the boundary, u is constant, it's equal to 0, and so the tangential derivatives are always 0. And du is in the direction of the normal. Okay, so that's kind of a long way of saying that the boundary is a level set at height 0. Okay, so what we're finding here is that the tangential part is given by let's go back to up here, is 1 on u d2u minus, well, tangential part okay, this df is in the direction of the normal. And so these guys are going to be 0. And this one here is a curvature term. Okay, so this is and here kappa is the curvature of the level set, which of course is just the curvature of the boundary. Okay, so this is positive. Okay, and we should also check out what the Hessian is doing in the normal directions. And this is given by so the same thing, but in normal directions here. So this one is just the length of the derivative of f. This one here, now we can use our equation for u here and write this one, the normal part of the Hessian, as a Laplacian minus the tangential part. Then we can use our equation. So this is minus lambda u plus vu minus so here we've got our eigenvalue. And well, we can get rid of our u, that's potential. And here we've got a kappa term. And the point of all this is that oh, sorry, I should have collected these guys. That's right, this is minus df. Okay, the point is that these are all positive. These are maybe not positive, but these are bounded. And this df is becoming huge near the boundary. So near the boundary, this is all going to be less than or equal to 0. So we don't need to worry about what's going on with f near the boundary. So f is certainly concave. Okay, so that's that step. So our next step is going to be trying to show that f is concave on the interior. We don't exactly do that. So let me tell you exactly what I am going to do. Okay, and the reason why I'm doing this is because I think it's a really nice technique which sort of uses maximum principle ideas, and it tells you, well, the idea is that you assume that you're at some maximum of a function, and then you can use that assumed maximality to really say quite a lot about your function. So what I'm going to do is consider the Hessian d2f as a function on the tangent space. So we're going to consider it as a function from omega cross S1 to R. So it takes a point in omega, so that's the point at which we evaluate it, and two tangent directions, and it maps them to a real number. And we've just shown that that this is non-positive near the boundary. So if this is non-positive everywhere, then we're done. Let's suppose that we have a point x0 in our domain, and some direction which we'll call E1, where this has a positive maximum. And in fact, what I'm going to do is I'm going to set g of x is equal to the Hessian evaluated at x, but just in this direction, E1. So So what I'm doing here is I'm starting off with the Hessian and I'm saying, okay, let's suppose it's got a maximum in some particular direction. And then I stop thinking about it as a function defined on the tangent space, and I go back to thinking about it on the domain, just defined on the domain omega, but restricting it to that direction in the tangent space. So what we have is we have g of x naught, which is equal to this maximum d2 f at x naught e1 e1, and this is going to be greater than or equal to d2f at x. And because we're assuming that this is the maximum, also over all other tangent directions, it's also going to be greater than this. So for all x and here. Okay, and we use coordinates, orthonormal coordinates, defined by this choice. And because we've chosen this point to be a maximum, E1 is going to be a eigenvector of the Hessian at x naught. And so what we have is that d2f at x naught of e1 e2 is equal to 0. Okay, so e1's kind of diagonalized the Hessian. And okay, so at this interior point of this interior maximum x naught of g, we have the gradient of g is equal to 0, and we have the Laplacian of g is less than or equal to 0. And so we can calculate these, and we find that 0 is greater than or equal to, and now we just take the derivative through. And so we get derivatives of Laplacian of f. And we know what Laplacian of f is because we've worked out the elliptic equation satisfied by f. And so we get and a bunch of things drop out, but so we don't get any derivatives of the eigenvalue, for example, but we do get the derivatives of the potential V, and we get derivatives of df, and so we get this is minus 2. We get here we get d E1 F d EK F all squared, and we get a third derivative d EK or D1 of F. Now, this, if we stare at it long enough, we can realize that this is a gradient of G term. And so it's equal to 0. And this term is well, it has a sign. But we're actually not going to conclude anything here yet. We're just going to conclude that that this term here, oh no, sorry, let me go back. What's going on with this term here is that we have this this kind of diagonalization of the matrix here. So in fact, the only term that comes out of this is a DE1F. Sorry, I've made a mistake here. This should just be a second derivative. This is due to this. Okay, so this has told us that at this maximum point, we've got this this inequality for G. This is G here. So we've got D2F at X naught this is G squared. This is always going to be greater than VE1. So the second derivatives of the potential. And we can bound this by writing this as the minimum of V. So that doesn't look too bad. And because we sort of assumed that G was going to be a positive maximum. And, you know, here V has some minimum, so we know this has to be positive. It doesn't look so interesting. And this is kind of the crux of the proof here. The final step is to use a continuity method to find a counterexample or contradiction. And, you know, this has already gone on for some time. So I'll just briefly describe how we do this. We interpolate between the problem on a known domain and our given problem that we're interested in. And so our known domain here will be the ball with the potential given by x squared. So and at t equals 1, so t is a parameter here, is just our general domain omega, and whatever potential we're interested in. Just call that v. And so we write down the problem Laplacian of u t plus vt ut is equal to lambda t ut on omega t. So this will be omega 1 up here. Omega naught is equal to br. And so we can interpolate the potentials in a pretty explicit manner. We can just say Vt is equal to 1 minus t V naught. This is V naught, it's x squared, plus t V1. And this is a convex potential. And it's actually strictly convex for t less than 1. And we can similarly interpolate the domains. Such that it preserves this convexity. And there's actually a very explicit way you can do this using the support function. Okay, and now there's just something that's kind of a fact. Is solutions to this problem with the parameter are really strongly continuous. So let's call this one blue star. And when I say they're continuous, I mean, I think they're continuous in C21 and probably maybe even something better. So they're continuous under perturbations of the potential, and they're also continuous under perturbations of the domain. And so what we do here is we take our known problem over here at t equals 0, and we say, okay, we know that our property holds at t equals 0 because this was the example we had before, and by ODE methods we can show that our solution at t equals 0 is not just log concave, it's concave. And then we go along and say, okay, why don't we find the first point as t goes along here at which this property fails to hold. Okay, so let me write this down. So at t equals 0, we have d2f. In fact, d2f is less than 0. So this is ft. Ft equals log of ut, t equals 0. So what we do is we suppose that t0 is the smallest t0. Well, actually, the first t0 at which this fails to hold. So actually, I've got something stronger here. Okay, and then this gives us the contradiction because we have, there exists some sort of x0 E1 such that d2f t0 at x0 in some direction E1 is equal to 0. But the problem is we have our previous estimate here. Which is actually that at such a, if we assume this is a maximum point, which it has to be if this is the first one, then we have this inequality here. Okay, and so because our interpolated potential here is actually strictly convex, this is going to be strictly positive. Let's call this yellow star. Okay, so this contradicts. Okay, because okay, so let me fix up a few loose points here. Suppose, okay, let's suppose that T0 is less than 1 here. We might have just not strict convexity at t equals 1, because we're not assuming that the V we're interested in is strictly convex. And if we look at the way we defined V, we can see that as long as the V we're interested in is convex, and our original V naught, which was like x squared, is strictly convex, and the strict convexity will go across for all t less than 1. Okay, so then we're done. Okay. Yeah, so that's the proof due to essentially to Yao and his group. And there's some more proofs and more approaches there, and I'm hoping to say a little bit about those in the subsequent days. Yeah, I'm going to finish there, but if you have any questions, then please ask them.
Okay, I'm not sure if you can hear me.
Yeah, I can hear you.
Okay, I had a problem